Hello, and welcome to today's presentation on Hardware Aware QAOA algorithms for honeypot traffic partitioning on 100 plus qubit systems using the IBM Quantum Processor. My name is Casimir Dikasadis. I'm the Director of the Cybersecurity Education Programs at Marist University in Poughkeepsie, New York, where I also run the quantum computing research effort. Today's work was completed in collaboration with my student, Robbie McDonald, and also with Professor Cameron Cogburn at Rensselaer Polytechnic Institute in Troy, New York. Today's presentation is given as part of the ICEQT conference for 2026. To begin with, after a short introduction, I'd like to talk about the current hardware architectures that we'll be looking at in this presentation and review some of our prior work on QAOA optimization algorithms. We'll formulate the problem in terms of a weighted max cut algorithm, working with some temporal bipartite graphs of denial of service attacks against a series of honeypots that we've developed. We're going to be looking at scaling and overhead for several different types of IBM quantum architectures as part of a hardware feasibility study. For more details, I will refer you to our full paper in the conference proceedings and the references which I'll be citing throughout today's talk. To begin with, we're going to be considering three different IBM quantum computing hardware architectures, namely Boston, Miami, and Rensselaer. The IBM Boston architecture uses the Heron R3 processor with a heavy hex architecture, 120 to 140 qubits in practice. IBM Miami uses the Nighthawk processor with a square lattice up to 120 qubits. And the IBM Rensselaer system uses the Eagle processor with up to 127 qubits. Since our algorithm allocates one network attack node per qubit, we'll be looking at feasibility denial of service attacks up to a data set of about 110 nodes in scope. Now, in our prior work, we've looked at a series of honeypots for SDN controllers, DNS, and so forth, all of which collect data off the live internet. That data set is geolocated. We can then partition denial of service traffic and DDoS traffic versus non-attack traffic, map those results into hive plots or matrix formulations as shown here. We've implemented the max cut algorithm to classify inbound traffic to our honeypots as either attack traffic or benign traffic. And our prior work has shown a significant advantage in using QAOA as the optimization algorithm as compared to VQE or other implementations. We are formulating our optimization problem in terms of the weighted max cut algorithm. As you can see, this is a version of a quadratic unconstrained binary optimization problem. We have a graph in which each node represents an IP address which is attacking our honeypot, and every edge has a weighted value which is proportional to the strength of that attack, if you will. It tells us whether or not that attack is coming from a legitimate source or a DDoS attack. Our goal is to partition the input traffic into two sets, attack traffic and non-attack traffic. We do this by using a weighted max cut algorithm, which attempts to optimize the size of the cut value when we split the data set in two, as shown here. In this work, we're going to be focusing on graphs from our existing honeypot data. This is labeled data, and we know a priori whether events are attack traffic or not. Edges are created between attack events and given appropriate weights, as illustrated by the equations on this slide. We're going to be using a total of 4 data sets for these calculations with respectively 16, 32, 66, and 110 nodes total. This table summarizes the breakdown of those data sets. For example, the 110 node data set contains 90 DDoS attack events and 20 benign events. We're going to define the max cut cost ratio in a fairly standard way as shown here. The class defined reference cuts every edge in an attempt to maximize the value of the cut, and we compute an optimized value as shown in this expression. Now in our experimental method, we're going to be comparing our architecture and the QAOA algorithm runs against 3 classic baselines. If a quantum hardware run can't outperform random partitions on these baselines, then it's not considered useful as a proof of principle. So the baselines provide a sanity check. They calibrate the benchmark graphs and fix the scope of our comparison. The 3 benchmarks we'll be using are respectively best out of 1,000 random partitions, a multi-start greedy local search algorithm with 100 random starts, and a simulated annealing algorithm with 100 reads at 1,000 steps per read. First, let's look at a scaling study for the IBM Boston architecture. This was selected because it gave us the highest mean cost ratio among the 3 different IBM backends, and because it beats the best of 1,000 random baseline for more of the 110 seed datasets than any other backend. You can see here a comparison of several metrics against our 4 datasets. In particular, I'll draw your attention to the hardware cost ratio, which is highlighted in red. The mean cost ratio decreases as we go from a 16-node dataset to a 110-node dataset. That's expected for a fixed shallow QAOA circuit and optimizer budget. The hardware runs illustrate the QAOA beats the best of 1,000 random objectives for 20 out of the 21 scaling runs, meaning only one of the 6 attempts to use H110 did not beat the reference. Continuing our Boston scaling runs, we looked at the different cost ratio curves, and in particular we're going to highlight the matrix product state simulator, MPS results, for cost ratio and for balanced security as indicated in this table. The 2 cost ratio curves track each other within the sample standard deviation across all 4 datasets. We note that the performance plateaus well below the class-defined reference objective, reaching about 74% for the H110 dataset. There is some residual difference attributable to hardware noise and some other factors which are described in more detail in our total paper. The next slide shows the QAOA circuit routing and transpiler overhead for IBM Boston. QAOA cost layers require 2 qubit interactions corresponding to the edges on the max cut graph. In real hardware, those interactions have to map onto the back-end coupling graph, so routing can add substantial 2 qubit overhead. The 2 qubit count and the estimated swap equivalents, which are highlighted here, increase substantially as we go from a 16 qubit to a 110 qubit system. And we note that the growth is not strictly monotonic because it depends on a number of factors, including graph structure, layout, and number of interconnections that we can execute in parallel. Continuing our discussion of Boston QAOA with classic baselines, this table compares the Boston QAOA hardware results against 3 classical baseline objectives that we discussed earlier. You'll note that there are significant variations for a number of these terms, but as shown before, QAOA continues to exceed the best of 1,000 random baselines in 20 out of the 21 runs on Boston. These graphs go into a little more detail for the H110 dataset, the largest dataset that we analyzed. First, in the upper left, we see a hardware architecture comparison between Boston, Miami, and Rensselaer, looking at things such as cost ratio and balanced activity. The lower right graph goes into more detail on the routing and overhead comparison between Boston, Miami, and Rensselaer. You'll note again the circuit depth can vary significantly and does not change monotonically as we discussed on the prior slide. Moving on, we're going to compare the 3 IBM quantum backends for our largest dataset with 110 total points. As you can see from the highlighted elements in this table, the backend choice affects objective quality and security quality significantly, even when other factors are held fixed. The mean cost ratio was highest for IBM Boston, for example, whereas the mean balanced security was highest for IBM Miami. This indicates the importance of reporting all the statistics in order to get a full picture of how the hardware is behaving. In summary, we've talked about mapping real honeypot, DOS, and DDoS attack events through a weighted max cut benchmark and a QAOA circuit onto 3 types of IBM hardware using 4 different size datasets. The results demonstrate that a shallow QAOA algorithm can execute 100+ qubit cybersecurity-derived max cut problems on currently existing hardware. The backend architecture affects objective quality, security quality, and routing overhead, even when we hold other things constant, like the logical graph and algorithmic settings. We also observe that the max cut cost ratio, attack recall, benign preservation, quarantine precision, and balanced security should all be reported as separate metrics. Simple classical heuristics can also be used to solve this problem, which is why it makes a good hardware feasibility and architecture benchmark study. We plan to do additional work in this area in the future, including label-free graph construction and energy-aware cost for solution studies as some of our next steps. I'll refer you to our full paper for additional details. Thank you very much for your time.